Hey everybody. Today we're getting into Taylor series. Taylor series give you a very powerful technique for computing power series for given functions. So let's call that function f of x. We're trying to find a power series for it, so something of this form. Our whole goal is to find a formula for c sub n. It's okay if that formula involves n, and it probably should involve f of x as well. We expect those coefficients to depend on the function we're using. How do we find those coefficients? Well, the first one's easy. If I plug x equals a into the power series, all of the terms of the power series are going to go away except for the n equals 0 term. When n is 0, I get c sub 0. Therefore, c sub 0 is f of a. I'm going to get the other cn's by doing some derivatives and then plugging in x equals a. Let's get more specific about that. Here's the power series with some terms written out. I think that'll be helpful for our intuition. I take a derivative, term by term. We have a theorem that says when you have a convergent power series, you can differentiate just the way you would want to, term by term. Now you can see that if you plug in x equals a, everything's going away except for the c1 term. Therefore, f prime of a is c1, or saying it slightly differently, c1 is f prime of a. We now have a formula for c sub 1. Let's do one more. I want to do f double prime, like so. Plug in x equals a. Everything goes away, except now for the c2 term. Solving it for c2, I get that c2 is 1/2 f double prime of a. Okay, let's try and generalize this. The idea to get c sub n is to take the nth derivative and then plug x equals a in. And then everything will go away in that power series except for the constant term in that new power series. And that constant term is going to be the one that corresponded with c sub n x minus a to the n in the original power series. When I take those n derivatives, the first one gives me a factor of n, the second n minus 1, the third n minus 2, and so on. So after taking those n derivatives, I'm just left with c sub n factorial. Overall, if you take the nth derivative of f and plug in a, you get c sub n factorial. Solving that for cn, I get this, the nth derivative of f at a over n factorial. I've now accomplished my goal. I have a formula for c sub n in terms of n and f. Plugging that back into my original power series, I get what we call the Taylor series expansion of f of x at x equals a. The sum n equals 0 to infinity, nth derivative of f evaluated at a over n factorial times x minus a to the n. This is very, very useful. If you can take derivatives of a function, you can compute coefficients for its power series. However, you should be careful as you use this. Taking lots of derivatives of a function is potentially very difficult and very time-consuming. If you have a simpler technique at your disposal for computing a power series, you should use it. For example, we know that for rational functions, where we have one polynomial over another, we can frequently make use of the geometric series. Sum x to the n equals 1 over 1 minus x, when absolute value of x is less than 1. Let's do an example. Find the Taylor series for f of x equals 1 over x with center a equals 2. So we need to start taking derivatives, and then we need to start plugging in x equals 2 into those derivatives to get these coefficients. Let's write f of x in a slightly neater way, x to the negative 1. Now the derivative is negative x to the negative second. The second derivative is 2x to the negative third. The third derivative is negative 6x to the fourth, and so on. Notice that we're starting to see factorials out in front as coefficients. That's nice, because when I actually compute the coefficients, c sub n, I'm going to be dividing by factorials. Okay, so to get cn, I plug x equals 2 into that nth derivative and divide by n factorial. I end up with 1/2, negative a fourth, 1/8, negative a 16th. So the first few terms of the Taylor series are like this. I just took those coefficients and put them in front of the x minus 2 to the n for each different n. All right, so already that's a little bit of an approximation of 1 over x. just using a polynomial. Let's try and be a bit more general, because I'm seeing a pattern here, right? 1/2, negative a fourth, positive an eighth, negative a 16th. So I'm doing -1 to the n to get an alternating series. And notice when I use n equals 0, that's going to be positive, so the first term of my series should be positive. The denominator is going to be always a power of 2. So that's why I have 2 to the n plus 1. I'm wanting to start with a 2 in the denominator, not 1. That's why the n plus 1. When I plug in 0, I want to get 2. Finally, of course, I have the x minus 2 to the n. Just standard power series stuff. So this is great. This is the full Taylor series expansion for 1 over x at x equals 2. But I don't think we're done yet. In order for this to really be a complete answer, we should be able to say the interval of convergence of this power series. In other words, for what values of x is this equality actually true? Almost always, we're going to do intervals of convergence using a ratio test. I take the limit as n goes to infinity, an plus 1 over an in absolute value. So this whole mess. Fortunately, this simplifies very quickly. The -1 to the n's go away because of the absolute values. Almost all of the factors of 2 cancel, and almost all of the factors of x minus 2 cancel. Now, the ratio test says that the series will converge when this is less than 1. That is, when the absolute value of x minus 2 is less than 2. In other words, from 0 to 4, the open interval. The ratio test says that this will diverge when the absolute value of x minus 2 is greater than 2. It says nothing when this limit is equal to 1. In other words, when x equals 0 or x equals 4. We have to plug in those endpoints to the series manually and see if we get something that converges or not. So let's start with x equals 0. When we plug that in, here's what we get. The -2 to the n, I am interpreting as -1 to the n times 2 to the n. And so then the -1 to the n times -1 to the n is just going to be 1. And 2 to the n over 2 to the n plus 1 is just going to be 1/2. Overall, the series just becomes sum n equals 0 to infinity of 1/2. And of course that diverges. Every time you're just adding another half. Similarly, if you plug in x equals 4, you get the sum from n equals 0 to infinity of -1 to the n over 2. So when n is even, this is a half, and when n is odd, it's -1/2. So this series is just going to alternate back and forth between 1.5 and 0, because you add a half, subtract a half, add a half, subtract a half. It does not converge. Overall, the power series that we found before, this Taylor series expansion, is going to converge for all x values between 0 and 4, not including the endpoints.